I built a robot that follows noise using a robot starter kit and designing and building a custom microphone sensor circuit. Here's how I did it. My goal was to compare the signal from two microphones. Sound hits one before the other. So I should be able to use the delay to decide which way to turn. Printables created a contest to remix the Otto robot from HP Robots. So I ordered the starter kit. It comes with an ESP32 board, some sensors, motors, O-rings, and a battery. But the kit has no body. The idea is that you design and 3D print your own chassis. So I started by designing a wheel hub to mount the O-ring as a tire to the continuous RC servo motor horn. I used Onshape to make a simple hub with a channel for the O-ring to sit and a shoulder for the horn. It took 2 tries to get the right diameter for the O-ring. Too small and it falls off. Next time I'll skip the support. It's really annoying to remove. You want just a little bit of stretch to keep the O-ring tensioned. With the wheels done, I laid out the rest of the parts to visualize the chassis. I was going for a practicality. I just needed to hold the motors, battery and ESP32 board, and a breadboard for my microphone circuit. I also tried to minimize the print volume for a fast print. Again, it took 2 iterations to get right, and that's the point of 3D printing, to rapidly prototype and test ideas. Even then, it takes a while to print. I've built a small number of robots like this, and they work best with the drive motors in front and a third point of contact with the ground in the back. You can use a chair-style caster or a ball caster, but I find the best solution is a plastic spoon. When rapid prototyping, don't be afraid to use what you have around, including hot glue, especially for little robots like this. I made sure my breadboard fit on the back of the robot, that way I can upgrade my sensor in the future. I programmed the ESP32 to do a test drive to validate the design. I used a generic MicroPython binary on the Otto's board and used the Thani IDE to program it. It made it really easy to quickly write test code and check things out. Then I made some adapters to hold the microphones, using some wood vegetable skewers. I used my nLab to power the sensor circuit and visualize the signals. I built 2 mic circuits with a 2.5 volt bias and a small gain. Using a dog training clicker, I verified that the mics received sound at different times, usually by a millisecond or 2. So I sacrificed 2 of the Otto cables to connect the breadboard to the ESP32. I used hot glue as strain relief for the fragile solder connections. With the sensor powered by the Otto, I double-checked that it still worked. It's really important to test as you build, to catch bugs and visualize the data your code is going to work with. The nLab is really helpful for that. The last step was programming the ESP32 to read the mic signals as fast as possible and determine which mic heard the event first, and then turn in that direction. It certainly isn't perfect, but I think it shows the potential for a variety of custom sensors for the Otto. Thanks for watching. I posted the code on a blog post at getnlab.com. You can find the link in the video description, as well as a link to my entry to the Otto Remix contest, where you can find the step files to my 3D printed parts. If you want to learn how to design and build your own circuits, consider supporting nLab at getnlab.com, and check out our educational videos on YouTube, TikTok, and Instagram.